Thank you for a nice introduction. My name is Natalija Katic, and I'm a PhD student of electrical engineering between Belgrade and ETH Zurich. And the main focus of our research group is the neuromodulation. How to design the specific neural devices and the way to talk with our nervous system in order to try to restore some missing function or sensation. And computational modeling have been one of our approaches to deal with the issues. Sorry, it doesn't work. Okay. When walking or maintaining balance, humans are relying a lot on the sensory feedback. And the group of patients where you can see really the importance of that sensory feedback are the amputees. Currently available devices do not provide sensory feedback, and while using them, people are developing issues like this. They have very asymmetrical walking, as you can see, which leads to higher metabolic consumption while they are doing it. On the other hand, you can see how they're very slow while walking. They're not confident in the prosthesis. And that leads to the things like this. So they have very high risk of falls. And we believe these issues can be addressed by restoring sensory feedback. And a lot of different groups have been tried to do it artificially. And electrical stimulation have been one of the approaches that showed very promising results. Naturally, tactile feedback is transmitted via mechanoreceptors, and there are 4 types of them that are clustered based on the specific stimuli that they're transmitting, the way how they're responding to different stimuli, or the area they're covering on the foot sole called receptive field. And while going a step further to restore tactile feedback, we're dealing with several challenges. The first one is by looking at the more neuroscientific side, we are still limited, we have very limited understanding of the afferent activation. Even though electrophysiological recordings are able to reveal how tactile feedback is represented in afferent populations like microneurography technique, this is still a very difficult, expensive, and time-consuming procedure. And more importantly, it is limited to very stationary conditions. So the patient needs to stay still and do not move. On the side of the technology, we are still missing the proper language to speak with our nervous system. And also, my group have been tried with neural stimulation to restore sensory feedback, and we achieved like spatially selective sensory feedback, which improved motor tasks and reduced metabolic consumption. However, the stimulation strategies that have been tried still induce range of sensation, and they're often paresthesia-like. So reporting natural sensation is very, very rare. And in order to go a step further in dealing with these issues, we wanted to make a model that could create the neural responses of afferents in the foot sole, and we called it FootSim. So how we started from this? So we first divided the foot sole into 13 different regions, depending on their mechanical properties, and also densities of different afferents are different in different regions. We incorporated all 4 types of mechanoreceptors, so the user can place either a single afferent or the whole population of it, and then the user is creating a mechanical input. That mechanical input is given to the model as a distribution of the pressure that is stimulating the sole of the foot. So that information is entering in the first part of the FootSim model, which is mechanical one, and it incorporates specific mechanical features like hardness. So we are trying to mimic how the skin is changing, how it's deforming, and how that stimuli is propagating through the skin. These stresses that are calculated entering the second part of the FootSim model, which is mimicking the spiking response of specific afferents. And as the output, we are getting which afferents are activated on which place on the foot sole with which firing rate. And this second part has specific 11 parameters, and we fitted these parameters using real human microneurography data that are responses to sinusoidal mechanical stimuli. So what we were trying to fit these sets of parameters for specific afferents in order to minimize the difference between modeled and the empirical firing rates. So before I start explaining how you can use the FootSim model, first to recapitulate the features of it. So we incorporated all 4 types of mechanoreceptors and then tried to validate, is it really giving realistic outputs? So we first saw that the receptive field sizes have the same range like modeled and experimental one have very similar values. On the other hand, we tried the ramp and hold stimuli to apply, since that is the stimuli that is used to classify 4 types of afferents. And we saw that we are having very realistic result, which means that our model is able to generalize, even though it's not fitted on this type of stimulation, it can adapt. Then very important, it's easily to adapt to different group of patients. For example, we know that patients with diabetic neuropathy develop some different mechanical features like higher hardness of the skin. So you can easily change that in the model and adapt it to a specific person. Also, it's robust, so moderate jittering of specific parameters do not drastically impact the accuracy. And most importantly, this is very simple plug and play tool that could help us using it for different applications in neuroscience or the neuroprosthetics. If we look at the neuroscientific side, as I said, we can apply any kind of pressure profile and transmit that to the afferent activation. So for example, we can record, sorry, it didn't work. We can, for example, record the pressure distribution while the person is walking and immediately see the activation of these afferents. And by using that, we can actually analyze how different afferents are activated during realistic dynamic conditions, like it's walking. So to see which afferents are activated in which segment of the walking cycle, for example. So that can partially overcome the limitation of current recording techniques and give us understanding more about the role of the specific afferent types. We envision the usage of the foot sim in the neuroprosthetics, and this is how we see it. So for example, you have the amputee with a prosthesis, and under prosthesis, we can put the sensorite insole and use that information to create the pressure profile that we are giving to the foot sim model and have the afferent activated as the output. We can use that to create biomimetic stimulating paradigms, and that part is a project, let's say, in per se. So I'm giving just one example how we can do it. For example, we can take a peristimulus time histogram of activation of all afferents and use that to modulate the frequency of stimulation. This is just one example. We are sending that to neurostimulator and then using like specifically designed electrodes, which can we optimize, for example, using hybrid modeling. We are trying to restore close to natural sensations. Since this is, we were insisting on opportunities and challenges that computational modeling can give, I would use this time to just summarize and see what are the challenges in my work that computational modeling can address. So it helped us restore more natural sensation, which boosted the confidence, walking quality, and usability of the prosthesis. And on the other hand, it gave us the deeper understanding of the activation of afferents during like jogging or walking. How can computational modeling support my work or enhance my future work? This is what we were been doing recently. So it gave us the basis to create the biomimetic paradigms of stimulation, which we already tried in animals, and it showed that the biomimetic patterns are in the spinal cord similarly like processed as the natural touch. And we also applied that in humans, and the biomimetic paradigms really outperform that in the functional way, but also in the way how the person is perceiving that sensation. Regarding the data that would maybe help us and support our modeling efforts, of course, we need detailed human microneurography data, and always bigger data set means that you can be more precise. But more importantly, we would like to have spike trains and to try to fit our model based on this and not the firing rates, because if using that, we can be very spike timing precise. And regarding like more general key opportunities and challenges that we are facing in the field of computational modeling and neurorehabilitation. So what I see as the really big opportunities to have these predictors that are in silico plug and play ones that are usable in real-time applications. But we are dealing with several challenges, like we are always trying to find the trade-off between precision and generalization. So always dealing with, is it really valid to use the model? And on the other hand, computational models can be very time consuming. So we're always trying to reduce the complexity and the time needed for calculation. With this, thank you for this opportunity. The first one to talk like this, and I'm open to questions. Thank you.
Questions?
Great talk. I never really thought about the role of cutaneous afferents in the foot. I mainly think about it in the hand.
Yeah.
So this is very interesting. I was curious if you all have thought about, how this work can be combined with some of the other techniques, like the in the lower limb, the AMI procedure, right, where you sort of connect the antagonist muscles and you get this proprioceptive output to see how both proprioceptive feedback combined with this cutaneous feedback, what that does. Because I imagine sort of knowing where the foot strikes the ground or feeling that contact, and then also knowing if it's a knee prosthesis, right, where the leg is at any given time in the swing phase is really important. And so coming up with models that combine all of this information to do sort of better maybe stimulation and whatnot.
Yeah, we are focusing more on electrical stimulation. So we really didn't combine it with different techniques. What we were interested in, can we, with electrical stimulation, restore also proprioception? So as you know, it's very limited thing. People didn't really manage to do it. So we were then investigating, is there any limitation? And yeah, there is limitation in the spinal cord that we found. So they are interfering with each other. But no, we never thought about combining things, but maybe, yeah, thanks. That is a great idea. Thank you.
Great talk. So this is a question about how to deliver the electrotactile stimulation. My understanding about the electrotactile stimulation on the other body part, the optimized electrode placement, things like that is largely unknown. So I just wonder to what extent for the foot sole stimulation is kind of well mapped in terms of the electrode placement, things like that.
Yeah, regarding the spatial, like in the spatial way, how to spatially map the sensation. Yes. And I mean, we as a group are using also the hybrid modeling in order to define the proper position of the electrode, how to define the optimal design of the electrode and all of that. And yeah, depending on the type of the amputation, we can see what are our limitations. It is, of course, better if you can do it more like closer to the knee, closer to the foot. But if you have upper amputation, then you can use what you have. If I answered.
Hi, could I ask a question?
Yeah.
Yes, thank you. Very nice work. I think this is setting up a very nice physiological analog to what we need to know for sensation. But I think there has been perhaps an overinterpretation of physiological data in engineering work, where when we do our engineering work and we have our feedback system, we are always thinking of the feedback being continuous and continuously being taken into account, and error signals and all of that. But there's a lot of evidence that in biology, it's really more a matter of filtering out most of the sensory information and detecting salience, and then acting upon salience in a very lazy way. So the nervous system is inherently lazy. So John Guggenheimer and John Milton and others have been talking about these wait and act strategies, where you're actually not monitoring all of your sensory information all the time, but only react to discrete events that go out of the sensations that you're expecting from your priors. So I think considering how that information will be interpreted upstream is important. Do you have some thoughts about that?
Well, what we did is the testing in animals. So what we know is how it is interpreted in the spinal cord, but we do not have insights like how it is really processed in the cortex, like somatosensory cortex. We do not know. We only have what humans are reported. So they are reporting this type of sensation as the more natural one and the more like more pleasurable one, so not as paresthesia. And regarding the processing in spinal cord, when you come also in the dorsal root ganglion, what we observed that this signal is much more similar to the natural touch. So we were touching the cat and recording in the spinal cord and then comparing with biomimetic, and we have quite a good correlation. Again, it's not perfect, it's still electrical stimulation. So, but yeah, I think we are closer to it. Yeah,
I was just curious, how were you working with anyone or working with the pain and kind of seeing how the pain receptors, the nociceptors interfere with this process? Because of phantom limb pain is very common,
Yeah.
right? So I was curious, or just any other, like even residual pain in the stomach.
Yeah, this is a big issue. And when we were doing in humans, like with intraneural stimulation, we were able to reduce also the phantom limb pain by that. But this was not combined in this model. We didn't combine it in that way. Like we didn't merge the nociceptor part with the cutaneous one. But maybe we can think of expanding it.